Okay, so let's look at second order circuits. Plug my mic back in or on. So a second order circuit is one where you have multiple elements that can be charged and cannot be combined, right? So sometimes you can combine capacitors together, sometimes you can combine inductors together, but you can't combine capacitors and inductors together, and sometimes the circuits are laid out that you can't necessarily store it. So we'll have a case where we're looking at a simple RLC circuit, and this one is a pretty common one to analyze because you can represent a ton of real-world physical systems pretty easily with this. And it's an RLC circuit, but we've got, again, this really fabulous tool called Laplace. So we're not even going to do anything in the time domain. We won't even bother writing it in the time domain. We're going to immediately write the circuit analysis approach immediately in the Laplace domain. So this is an input voltage. Oops. That's an input voltage. We have our resistor, our inductor, which again is S times L, and our capacitor is 1 over CS. We did not include any initial conditions, and for the most part moving forward, we're going to assume that there are no initial conditions on our system. It makes the analysis of transfer functions much, much easier. So you can highlight that, no initial conditions. So then we're going to just apply a KVL loop. So we already have the minus to plus to minus, and plus to minus walking around the circuit. And if we sum the voltage drops and set it equal to 0, V of S is an input voltage, but it's a negative, right? Because it's a voltage rise. The remaining three are additive, okay? And we're just adding them in based on their voltage drop. So the voltage drop across this capacitor is the current through it times the quote-unquote impedance. The impedance is 1 over CS. So that's why the voltage drop is I times CS. We'll set that equal to 0, and then we're going to go ahead and collect terms so that we have this form here. Okay? So we have I of S equals CS, VS, blah, blah, blah. But what's more important is the denominator, because what we're going to start doing is in the time domain, right? The denominator in the Laplace domain always determine how the system responds, how long it takes for the system to respond. So one of the things that we actually describe that as is called the characteristic equation, because it characterizes the output in terms of its time response, how fast. Not necessarily its amplitude. That's almost a scaling factor. This is more of a time response. So this one we can look at it and we can realize that it would be better if we could factor out an LC term in there, because we'd like it to be S squared. So let's factor out 1 over LC. So we have V of S, CS, all over S squared. We're going to factor out LC here. So we're left with R over L times S. Right? Everybody see how I just factored out the LC? So I divide the C out, and then I divide the L, but there's no L term in there, so I've got to just factor that out. Plus 1 over L times C. Okay? And that's a little bit nicer. We also note here that we can cancel out the C terms, and then we're just left with that value. So this is essentially going to affect the scaling. The S term in here doesn't really affect anything, right? It's not going to affect the characteristic equation because that's the denominator. It's going to affect a little bit of the scaling factor, but what more dominates it is the 1 over L. And that's sort of summarized there. Okay? So now we're going to do the quadratic equation. And why do we do the quadratic equation? Because it gives us an idea of the roots, right? So if we have our quadratic equation, we know if the roots are real and equal, well, we should say real and unequal. I should have added that. I apologize. Real and equal or complex. Those are the only three cases you're going to have. Real and unequal, real and equal, and real and complex, essentially. So by looking at that, right, here is our final equation. Essentially, what determines all three of these cases, let's call this 1, 2, and 3, is what is going on here. What's happening inside that square root term, okay? So clearly, if r over 2l squared is greater than 1 over LC, or maybe not so clearly, what can we say about what's going to happen in the square root? Is it going to be a positive or a negative number? If this number here is bigger than this number, what happens under the square root? It's a positive number. What's the square root of a positive number? A real number, right? So I have a real number here plus or minus a real number, which means I'm going to get real and unequal roots. They may be negative, one positive, one negative, but they do not have any complex numbers there. So that is our case 1 when that's the case. And when we do that, right, we know that we're going to have S plus a number here. Let's call it S plus alpha or S plus A times S plus B, right? Because it's the plus and the minus, we know when we subtract the term, right, because it's negative R over 2L minus a number, that's going to be greater than R over 2L plus the number, right? Because this negative number here makes it a greater number. So what I'm trying to say is the number that you're going to see here, one of those is going to be greater than the other. If I take that back into the time domain, e to the minus at, e to the minus bt, one of those is going to take longer to reach steady state. It takes 5 time constants, so whichever has the bigger time constant is going to take longer to sort of reach a steady state point. So that's why it's called overdamped, because we've increased this value of R so much. We put so much resistance. What do mechanical engineers think of when they think of resistance? Friction, damping, right? We've made it so difficult for that system to respond to that energy that's flowing in the system that we've basically forced the system to have a lot of resistance, and it makes it going to slow down quite a bit. It makes the system response slow down. So we've damped the system down to the point where it is overdamped. It's taking longer than necessary to reach steady state. And that only occurs because I've increased that resistance value too much. It's too great. The next case is what happens if R over 2L squared equals 1 over LC? What happens under the square root term, or within the square root? Goes to 0, right? Yeah, so I have R over 2L plus or minus 0, which means my roots are still real, aren't they? But they are equal. And because of this case, right, where we have one case where we have a shorter time, but one where we have a greater time, that's going to have the fastest response, isn't it? It's going to respond the quickest. It's going to reach steady state the fastest. That is called critical damping. When I've dialed in the resistance so perfectly that it's got no square root term, and it's the fastest responding term. It's critical because if we deviate one way or the other, we sort of fall off that case, right? So ideally, you like every system to be critical, but in the real world, resistance just changes over time, inductance changes, things just change over time, which means that you can't control it. It's going to shift and you can't deal with it. So critical is the perfect case, but we're never perfect, so we always deviate. What's the next case? Well, the only other case is when R over 2L squared is less than 1 over LC. When it's less than 1 over LC, what happens under the square root or in the square root term? It's a negative number. What's the square root of a negative number? a complex number as an imaginary term. So then what I'm left with is r over 2l plus some j term, or plus or minus some j term. That means, what type of response does that mean? Well, if we have a real part and a complex part, what does that look like in f of t land? It's going to have e raised to some alpha t, and it's either going to be a sine or a cosine. So it is going to exhibit oscillatory behavior, right? It's going to oscillate. It's going to overshoot, then undershoot. Overshoot, then undershoot. Until the e to the minus alpha t reaches a point where it sort of shuts down the damping at that point, right? It's gotten a point where it's reached steady state, and so at that point, it doesn't continue to damp anymore. Okay? You will note, in the case when we have complex roots, anytime you're in the Laplace domain or working in the Laplace domain, you must have complex conjugates, right? The real part doesn't change, but the imaginary part will be a plus and a minus. So a conjugate means it's a complex conjugate. That means you have a positive and a negative j term. Okay? So those are the three cases: over, critically, and underdamped case. You do have some cases when r equals 0. What's that called? Oh, senior project mavens. When r equals 0, when you have no resistance, what does that become? You have no damping, right? R is equal to 0, so it's not underdamped at all. It's 0 damped. What happens when you have an L and a C and a no R value? Go back to the roots here. What happens if this equals 0? What happens if this equals 0? It's 0 for the real part plus or minus j times something. What happens here? Alpha is equal to, there's no real part. What does alpha equal? 0. So e to the minus 0 is 1. There's no damping. This is just an oscillator, right? Have you talked about that in 342? Where you built an oscillator circuit? And an oscillator circuit sometimes is a crystal. So a crystal, you know, like some of the, I don't know about today, but it used to be that some computers and phones and all that stuff, not phones, but computers or computer devices, if they wanted to keep track of time, they just had an oscillator inside the computer that they had a very specific frequency that it oscillates at, 50 megahertz, 1,000 megahertz, whatever it is, and then you just count the number of oscillations, and that's how you keep track of time. So it just oscillates at that constant frequency forever. So you build an oscillator by having no damping. Now the problem is there's no real-world circuit that R is equal to 0, so you always have to put a little bit of energy. But the crystals that they have do a pretty darn good job of having almost negligible resistance. That's why you can have a crystal inside of a device that can last for many, many years and continue to oscillate. But it doesn't last forever, right? Because it does have some resistance. So that's an oscillator. Here's a way of looking at something that has a damping, right? And so this is reaching a steady state that we're going to some current, some small current. We start off with a steady state value, and then we work our way, and then this is essentially, 5 time constants here. This is the case where, where am I? You can see that it peaks out, and it doesn't get quite as high, but it actually ramps down and reaches that value. If I look at case 3, you actually have an oscillatory response whose value steadies out at 0. Okay? So because of the underdamped case, you now have a sine wave or a cosine wave term that goes ahead and continues until the e to the minus alpha t starts to dominate and takes care of that. Okay? So all three cases. So let's look at my next slide, which actually shows you if it's critically damped. Oops, why is that cropping? Huh. I'm not sure why it's cropped. Well, this one clearly is underdamped because it doesn't have enough resistance and it oscillates out of the way. Can you tell which one is critically damped or which one is overdamped? The green or the blue? Let's do critically damped. Which one is the critically damped case? It's either blue or green. Why do you say green? Because it achieves steady state much, much faster, maybe not much faster, but faster than the overdamped case. Okay? So essentially all I did was I took an inductor and a capacitor, and you'll be doing that in lab on Monday. You're going to be tweaking your L and your your R, to go ahead and increase or decrease the amount of damping to get the response characteristic that you want. Yeah, I'm not sure why this has moved, but this one does an even better job showing you as it reaches a steady state value. So can you tell me which one is underdamped? Green, red, or blue? Remember, it has to have a sine or a cosine wave to be underdamped. So that's underdamped. Now, blue or red for critically damped. And remember, critically damped will achieve steady state faster than overdamped. So that is critical. And then over is the blue. And I'm not sure why that got moved around. I love a PDF. So we'll look at a couple cases where we have a circuit here. We have R equals 12, 2, and 4. And we'll look at the different cases, and I won't do all of the steps other than to write a generic equation, which we have here. And that's written in standard form, 20 times V over S times S squared plus RS plus 20. So I wrote this generically in terms of a value for R. And then we're going to just go ahead and start substituting in R. So we're going to put in R equals 12. Then we're going to go ahead and expand it out. S times S plus 2 over S plus 10. Do a bunch of partial fraction expansion. But what's important here to notice is I have two roots that are not equal, right? I have S plus 2 and S plus 10. Those are not equal. So that immediately should tell you that I am overdamped. Okay? And when you go back here and look here, you can actually see that I have two separate e to the minus t's, right? One e to the minus 2t, one e to the minus 10t. Of the two, which one's going to reach steady state faster, the 10t or the 2t? Because remember, it's t over tau, right? So is 1 over 2 greater than 1 over 10? So this one takes longer to reach steady state. It's 5 time constants, right? Which is 5 times 0.5. It takes 2.5 seconds, where the other one takes 0.5 seconds to reach steady state. Now let's do the other case where the number is awfully weird. 2 square root of 20, which probably already tells you that this is going to be critically damped. But if I look over here, I have two real and equal roots. When I do my math out, and I take the derivative just like we did for the exam, we end up with something that looks like this. So only one exponential, and its time constant is 1 over the square root of 20. Is that greater than or less than 1 over 2? It's less than, right? Because the square root of 20 is going to be something like 4 something, so it's 1 over 4 versus 1 over 2. So clearly, this one has a faster response for achieving steady state than the overdamped case. All right, and then the last case where we have 4, what do you know? We have complex roots. S plus 2 squared plus 4 squared, which means in our final equation, we have a sinusoid. Now you'll note that this time constant, tau, right, is equal to 1 over 2, which is slow, right? But why would we rather go with that than the other case? Well, take a look. It actually gets to steady state, or pretty close to steady state, if you look at the green, faster than it takes for the red, because the sine wave, right, is overshooting and undershooting, but it's getting there faster. So if you work in the process control industry, paper mills, pulp and paper, whatever you want, you almost always want an underdamped system, and the underdamped system is going to give you the fastest response time. A critically damped system would be ideal, but again, the process is going to change too much over time, so you don't want to lay your hands and just say, hope, for the best, this is going to work out. You're going to actually specify an underdamped system and go with that. And one of the things that some people do is called quarter amplitude damping. That's an older classical one, but that's one of the ways it actually looks at each successive amplitude is 1/4 the previous one. That used to be called ideal tuning. That was like the Ziegler-Nichols tuning. And I don't know if people who worked in the pulp and paper area, if they've done tuning like that, but most of the response characteristics you're looking for second order systems have this characteristic. Okay? Because again, it reaches steady state the fastest. You can tolerate a small amount of overshoot, small amount. So if you're filling up a tank, right, you obviously don't want to overfill a tank so water starts splashing onto the ground, because for the most part, if you work in a pulp and paper or process control, that water is just not regular old water. It might be super clean water, which means it's demineralized, deionized, all that stuff, or it might have some chemicals added to it. And what's a bad thing to do? Spill chemicals where you don't want it, right? So filling a tank, you might allow it to overshoot some level. So you don't want to fill the tank to 100%. You might want to fill the tank to, let's say, 80%, so you've got some capacity there. So as you're filling it up, it can ring a little bit and kind of even it out. So that's where you would stop it at, I don't know, 80%, and then you overshoot a little bit, and then it'll open and close because you always have a load on the tank, and you will actually start to drain out the tank, so it steadies out at 80%. Okay?
That's the same thing with batteries, right? Normally they charge, you can only ideally charge like 80%.
No, so the question is that the same thing with batteries? So batteries, you don't really work in the same concept. So Tesla suggests you don't overcharge their batteries, unless you're doing a long trip, because it changes life expectancy. That has to do with the chemicals and all the processes with the chemicals, and I don't know exactly why that does that. This is just once you've got it to 80%, stop. So with electrical flow, right, it's a very different experience. You're looking at it and you're making a discrete determination. Run it full out until you get close to 80%, maybe back it off a little bit when you get near 80%, and then when you hit 80%, go to 0. Where in the process control, you can't do that, right, because you're continuously draining water out of that tank, right? So the tank is being filled up, but some other part of the process is using it. So there's constantly water being added and removed. So it has to be more linear. It has to be more continuous. Where with batteries, with electric, that's the thing about electrical systems. They can almost always be discrete. And they're not really discrete, but they're so close to discrete, you can just make things easier. Like your cell phones, right? Or if you're in audio, like high power applications, why do you use Class D amplifiers? Super, super efficient because it's on or off. It may not sound great, but it's on or off efficient. With other real world systems, it's very difficult to get a real world system to be going 100 miles an hour and then go to 0 miles an hour and then go back up to 100 miles an hour. Where electrical systems, I can do this to the point where it'll annoy you. Right? How fast is that happening? Full on to off in the blink of an eye. Is there anything else in the world that can go full on to full off? Yeah, it just doesn't happen. Electrical systems, that's why we can cheat a little bit. And that's it for chapter 6. Got a bunch of homework, and you got a test. I'll let you out a few minutes early unless there's some questions. Got homework. I'll get a test redo if you decide to. Any questions? All right, I'm going to start processing the exam review now. Have a great weekend.